trying to hang, but you're going to not do as well holding the electrons together if you only have 8 protons versus 9. Now, if I had the choice of fluoride, oxide, or nitride, N-3, that only would have 7 protons in the nucleus, so that would be even a bigger radius. So the winner on this one is the oxide. Okay, and finally, last one, magnesium positive 2 or chloride negative 1. Which one do you think is bigger between those two? The negative ion is going to be bigger. Chloride gets bigger when it forms ion. Magnesium, over on the left side, it would get way smaller. Again, losing 2 electrons brings the electrons in really tightly to the, toward the nucleus. And then gaining an electron, that thing balloons out. That's going to be the winner between those two. Okay? All right, so that takes care of our periodic properties and ionic as well. Just one last thing that I need to go over with you. And this last thing is experimental analysis technique that I couldn't even tell you how long it's been around. Honestly, I majored in chemistry. This is back in the 90s that I was in school, and I had never heard of this in my life. And then in 2013-14, when the College Board decided they were going to change the curriculum for this class, they decided that photoelectron spectroscopy was very important, and they needed to put it into the curriculum and make sure. So I had to learn what PPS was. That's the abbreviation for it. So photoelectron spectroscopy is it's a technique, and I'll describe it in a moment. I know there's a lot of words on here. Give you a chance to write this down, and then I'll try to give you a picture of the way it works. Ready for the next part? So photoelectron spectroscopy, I'm going to just call it PES from now on. The word spectroscopy means that we're using light to measure something. You know, we use the spectrometers occasionally in this class. We're using light to measure concentration of things. Sujin, welcome back. Unfortunately, I had to take one of the desks out into the hallway, so there's this one that's open. Okay. So in this case, spectroscopy, the photoelectron spectroscopy is there to measure how much energy it requires to remove electrons from an atom. What they'll do is they'll take a small sample of an atom, or of an element, I guess, a few atoms of it, only a billion or whatever, I don't know, there's some small sample. And they'll shine light at it. And they'll start with light at a very low energy. So the low energy light will do nothing to the atom. So they'll be detecting it with this electric field, and they'll just be watching for the thing to ionize. So with the low energy light, nothing is happening. So they start cranking up the energy. They kind of sweep through a whole range of energies. And as they increase the energy of light on this sample, eventually they're going to get to a certain energy of light. Whatever the energy of light that they're shining on the sample, when it's equal to the ionization energy of that first electron that's going to come off of it, then the electron pops off and it loses the electron. In fact, they'll shine energy of light that removes the entire energy sublevel of electrons. Whatever energy that is, that will get kind of broken off. And so that'll cause the detector to recognize, oh, we've had some electrons come off of this thing. Then they continue to increase the energy of light that's shining on it, and then the next energy sublevel of electrons in from the one that just came off, then they'll come off. And so it will detect every single electron energy sublevel of electrons that come up, all the way down to the 1s, to the closest to the nucleus. Now, the way that the spectrum works, let's see, this last bullet point down here, the highest energy is to the left. That's what I'm going to have you see. You don't need to write anything down on this, but I just want you to look at it. When you have a PES graph like this, the highest energy is over on the left. It goes from low energy over here to the left where the high energy is over here. And you can see this on the x-axis, the scale. It's 0.1 megajoules per mole on the right. And as it goes left, 1, 10, 100 is a logarithmic scale, up to 1,000 megajoules per mole on the left. So we're going to have to kind of wrap our brains around that. It goes from right to left. So the outermost electrons are the ones that are easiest to come off. They're these electrons that are coming off here, represented by that peak. Then the next energy, energy sublevel or electrons in would be those, and then those, and then those. So the farthest left would be the electrons that are the most difficult to remove, which are the ones that are right next to the nucleus. The nucleus is like, hey, man, I'm hanging on to you. But then eventually they'll come off too with the highest energy required. So yeah, this peak would be the 1s electrons. This peak, I have this kind of hidden down here, that's 2s electrons. And then the next, by the way, notice the y-axis. The y-axis says the relative number of electrons that are coming off. So you can use this thing to actually identify an element. Because if these are the 1s electrons, you know there's 2 electrons in 1s before electrons start filling the next out. So this peak is the same size as that peak. So if there were 2 electrons there, being the same size, you know there's 2 electrons there in 2s. Now this peak is 3 times bigger than that one. That's the 2p electrons, where there are 6 electrons in 2p, 3 times more than there were in 2s. You with me? So that's how we read this thing, and it's there. 2p electrons, there's the 6 of them. And then once 2p is full, then we go out to 3s. Oops. There they are, 3s, 2 electrons. Now this last one, notice that this peak is not the same height as this peak. Each grid line looks like represents 1 electron. You got 1 electron, 2 electrons. This is 1, 2, 3, 4. So that's how we know, somewhere on there. That's how we know that there are 4 electrons out there in 3p, is because of the kind of the scale that was established by the rest of the peaks, that we knew how many electrons were. So this would be the PES spectrum of sulfur. As it goes from low energy to high energy, the first ones that come off are the farthest out away from the nucleus, which is the 3p, and then the 3s, the 2p, the 2s, and then finally the 1s. Okay, so given that, the next slide has an unknown. With the same reasoning, what element is represented by this PES spectrum? Now, bear in mind these double lines on here. You probably have seen this before. That just means there was a long gap where there was nothing happening, so they just kind of shortened it down with that line. This is often the case when you have a logarithmic scale. Take a look at this one. which element is represented by this spectrum? Yell it out when you think you know. Don't be shy. What element? These are 1s electrons, right? Farthest left are the closest to the nucleus, 1s, 2s, 2p, and 3s. Take a stab at it.
Magnesium.
Thank you, Justin. Magnesium is right. Were you thinking magnesium? We didn't want to say? Are you mad today? Johnny, you mad? You need a hug? Magnesium is right. Here's why. Because we know these are the 1s electrons. The 1s is always the farthest left, the highest energy to remove. So 1s, and then we have 2s, which is the same size. So it's 1s2, 2s2. And then this one, we just have to eyeball. You could even use your fingers. There's 2 electrons. So I'm going to go there, 2, 4, 6, very close. So that it would be 6 electrons, or 2p. And then this peak is the same height as that peak. So there must be the same number of electrons out there in 3s as there were in 2s. It would be 2 electrons in 3s, which takes us to magnesium. Yeah? So that's what we do with photoelectron spectroscopy is we try to identify what elements. And you might have a question that asks you to analyze something about an element. Here's another one. This was back when they introduced PES to the teachers of chemistry. They said, well, you know, there's a lot of people that won't even know what PES is, so they had to give a little tutorial. And so this is a whole, as you see, 50-minute webcast that explained what this technique was. And then they gave sample questions, like they came up with some questions. And this is a nice, easy one. What element is this? They give you even a multiple choice format for this one. Show me with your hand when you think you know what multiple choice letter it is. Okay, yeah. Rohit, yeah. Make the letter with your hands, or hands, right. Yeah. You guys are grumpy today. This is terrible. I feel horrible. I hope it wasn't me that made you mad. Ellen, did I do something to make you mad? No? Okay. I didn't give you enough chocolate? Is that what it was? I get cranky when I haven't had enough chocolate. I'm sad about that too. Yeah, so we're not mad, we're sad. Okay. I'll give you that. I saw a couple of you do one of these. That's correct. It is C. Yes. It's C because it is nitrogen. There's 1s. There's 2s. And how do we know how many electrons are 2p? Well, it looks like in this case, every 2 grid lines represents 1 electron. Yeah? So we have one. There's 1 electron. There's the second electron. There's the third electron. There's 3 electrons there in the 2p. That makes it nitrogen. Okay, so we can identify an element based on its spectrum. And then this one is kind of an interesting one too. I'm not crazy about the way the question is posed, but they're asking you to explain something now, but it's in a multiple choice format. Which of these choices best explains the positioning and intensity of the 2s peaks in the following spectrum? Now, I didn't even notice this until I had to look at this for a while, but it recognizes this one as lithium, and this second one is beryllium. And they're asking you to compare the 2s electrons only. You see the 1s is not even present. What about the 2s electrons in lithium and beryllium? It asks you to compare the position and the intensity in terms of the height. Take a look at these, and once again, when you think you know the answer, make the letter with your hands.